Hello, everyone. Welcome to the March 31st edition of Math 262. Reminder that you have WebAssign due on Friday. So before we begin, I thought I'd give you, before we begin with new material, I thought I'd give you two examples to do to find the interval of convergence for the following two series. All right, so you have to show the work, but you should find that the interval of convergence here is from -1 to 1. And the interval of convergence on the right should be from 0 to 2. All right. So today we're going to learn something new. We're going to learn about differentiating and integrating power series. All right, so part of the reason we like power series so much is they're incredibly easy to differentiate and integrate. You just integrate and differentiate each term. So that's a theorem. And it says if the function f of x is the sum of an times this quantity, which looks a bit like this. And let's say it has radius of convergence r. Then on the interval c minus r to c plus r, we can integrate and differentiate f. And furthermore, we have a formula for the derivative of f. So I just use the power rule. And the power rule up here will tell me that the derivative should just be an times n times x minus c to the n minus 1. And that's the derivative. And the integral is done in a similarly easy manner. So we have the integration constant. And we add from 0 to infinity an times x minus c to the n plus 1 over n plus 1. All right. So what we notice is that the radius of convergence of the series obtained by differentiating or integrating is the same as the radius of convergence for the original series. All right, the only thing that can change is what happens at the endpoints. So I'm going to do an example where we look at the function in just a second, and we look at the behavior at the endpoints. But before we do that, let's take a look at some series and their derivatives and see if you can figure out what the functions are. So let's look at these functions and practice differentiating and integrating them, and then we will work on intervals of convergence. So let's look at the function x to the n over n factorial. So let's do f prime. Well, we see that the derivative of 1 is just 0. The derivative of x is just 1. The derivative of x squared over 2 is just x. The derivative of x cubed over 3 factorial is x squared over 2 factorial. And what do you notice about these two series? You'll notice that they're exactly the same. What function is f? What function do you know that's equal to its derivative? And you can probably all figure out that it must be e to the x. All right, let's look at another example now. I want you to integrate the following series. It's x over 3 raised to the n. Well, go ahead and do it in your notes, but you just need to integrate each term. So we have x to the n over 3 to the n. Well, we can integrate that. It should be the sum of x to the n plus 1 over n plus 1 times 3 to the n. And don't forget that you need to have a constant out front. And so that's how we integrate. It's as easy as that. So now we're going to examine what happens when I integrate and differentiate a series. And I'll do one of them and you'll do one of them as well. So let's look at the function f of x is the sum of the series of x to the n over n squared. I think you actually did this one already, but we'll take a look at we'll do it now. So, well, we know that un is x to the n over n squared, and that un plus 1 is x to the n plus 1 over n plus 1 squared. And then what we can do is we take the limit as n goes to infinity of un plus 1 over un, which is x to the n plus 1 over n plus 1 squared over x to the n over n squared. And if we simplify that a little bit, what we'll get is we'll get x times n squared over n plus 1 squared. We take out an absolute value of x. And I think we all know that this piece here goes to 1 as n goes to infinity. So it equals well, ignore that big red line there. It should equal the absolute value of x, which must be less than 1. So this tells us that we're going to converge from -1 to 1, and we need to check the endpoints. So check the endpoints. X equals 1, x equals -1. So we'll do x equals 1 first. So what that tells us is the sum becomes this sum. Which converges by the p-test. With p equals 2. All right. So let's do x equals -1. So I'm going to show you something that we maybe have not done a whole lot. If this is my term an, we know that if the sum of the absolute values of the a sub n converge, this will tell us that the sum of the a sub n's converge as well. So if a sub n is -1 to the n over n squared, this tells us the absolute values of the a_n's are 1 over n squared, which tells us that the sum of these guys converges by the p-test. And then since the sum of the absolute values of a_n's converged, this tells us that the sum of the a sub n's also converges. And that's because the sum of the absolute values of the a sub n's converged. You could also have used the alternating series test. But anyway, what this tells us anyway is that our interval of convergence is from -1 to 1, where we include the endpoints. So here's my function f again, and we found that the interval of convergence was from -1 to 1. So it's not so hard to compute the derivative. You just take the derivative of each term. This becomes n times x to the n minus 1 over n squared, which is the sum from n equals 1 to infinity of x to the n minus 1 over n. And similarly, the integral of f of x is the sum from n equals 1 to infinity of x to the n plus 1 over n plus 1, and then times 1 over n squared. So the last thing I have you do is find the interval of convergence for the derivative of f and the integral of f. So one thing to keep in mind is you already know that the radius of convergence is 1 for f prime and the integral of f. The radius of convergence does not change when you take the derivative or the integral. So that means all you need to do is to check the endpoints of plus and minus 1 for the series for f prime and the series for integral of f and see what you get. All right, let me know if you have any questions, and I will see you all tomorrow.